This lecture is on optimization. Optimization is basically word problems involving extrema, so word problems where minima and maxima are the solutions that you are looking for. So here are some examples before we talk about a general procedure. This is the so-called barn problem. You have 40 feet of fence to enclose a rectangular garden alongside of a barn. What is the maximum area that you can enclose? The idea being you do not need to have fence along the barn. And so we draw something. Here's our barn, here's our rectangle. If this is x, we know this will also be x because we have 40 feet of fencing. This must be 40 minus 2x. So our width is x, our length is 40 minus 2x. We want to maximize area, so therefore we need an area function. That's the key thing. The thing you're trying to maximize or minimize, that is optimize, is a function you need to have so that you can differentiate it. So here's our area function. So width times our length. You can distribute it. To find the maximum and minimum, as we know, we look for critical numbers. So I'll differentiate it, set it equal to 0, and I end up getting that x is equal to 10. If x is equal to 10, I know that my width is going to be 20. My overall area then will be 200 feet squared. Besides looking for critical numbers, that is where the derivative is 0 or undefined. Occasionally you'll have to check endpoints as well, though it is quite rare. Another problem is the open box problem. We start with a flat sheet and we remove squares, and then we fold up the sides of the box to make the sides of the sheet to make it an open box. Because this was a distance of 8, this will be now 8 minus 2x, or a minus 2x. Because this was a distance before of b was 6, when you take a corner off each side, this will be 6 minus 2x. So the length of our box is 8 minus 2x. The width of our box is 6 minus 2x, and the height of our box is x. Now what we want to do is vary the squares to try to get as big a volume as possible. So here we have big flat but not very high. Here we have very narrow but high, so there's some optimal value. This is a graph. The area is obviously getting smaller as x gets bigger. The volume peaks out somewhere. We want to find that spot. Here's a graph of the derivative of volume with respect to x, and you can see that where we have a maximum volume, the derivative goes from positive to negative as we would expect it to, and we want to find a place where that derivative is 0. So what we have here is the visual idea that the maximum volume comes when x is 1.131. Now let's go back and take a look at the calculus and a lot of the algebra behind it. So what happens is we have our volume is length times width times height. Our length was 8 minus 2x. Our width is 6 minus 2x. Our height was x. What I did was I factored out a negative 2 from each of these, and I put the x in front just because I thought it would then be easier for me to multiply everything else. You could use product rule to differentiate this, but I thought it would be easier to multiply all these pieces out. Then I take a derivative. I left the 4 because it's just a constant multiple. So v prime of x is equal to all of this. That's never going to be undefined because it's a polynomial. So we set it equal to 0. So we're solving this quadratic equation, which is going to require the quadratic formula. So there's all of that algebra. So we go ahead and simplify and simplify and simplify, and we eventually get two solutions, 3.535 and 1.131. So 1.31, that's the answer we want. Now, we know we want that answer for a couple of reasons. We could check that it gives us a maximum by doing things like the first or second derivative test to really justify it. We don't really need to do that. Remember, this volume is a cubic equation, and so it would look something like this. Now notice that the part we're seeing over here, this orange-brown, is just this part of the curve here. So the 3.535, that's down here. That's a negative volume. Clearly, that's not what we want. Also, that's outside the feasible domain of our problem. If x gets bigger than 3, then the width goes to 0. We have no width at all. So x must be between 0 and 3. If it's less than 0, you have no height. If it's more than 3, the width is gone. This is outside that feasible domain. So as far as a general way of going about this, a lot of this is the same for all sorts of word problems. Identify all given quantities and quantities to be determined. So what do we know? What do we want to know? And try to make a sketch. So good general advice for word problems. Write a primary equation for the quantity that is to be maximized or minimized. A lot of times it comes from geometry. And so yes, the thing you're trying to optimize, you need an equation for that, and that's called the primary equation. Now sometimes that primary equation is in terms of more than one variable, so you have to use one or more secondary equations to reduce the primary equation down to a single variable. Then I usually do step 5, that is, I find the maximum or minimum using calculus techniques, differentiation that is, and then after that I would go back to step 4 and find out what makes sense and what doesn't. What's the feasible domain? Determine which of the actual answers you get makes sense. So here we have a geometric optimization problem. We have this parabola f of x equals 4 minus x squared. We have a point 0, 2. We want to find the points on this graph closest to this point. So we're trying to minimize distance. If we're trying to minimize distance, we need a distance equation. So here's the distance formula from the point x, y to 0, 2. We know that y is equal to 4 minus x squared, so we plug it in here, and we can differentiate this. Now, in this example, rather than differentiate with the radical, they've removed the radical because it turns out it doesn't actually matter for this problem. Usually you cannot do that. I warn you against doing that on every problem. You can't. It saves you a little bit of time, though, in this particular one to do without the radical. You differentiate, you set it equals 0, and you get the value 0, and plus or minus rad through halves. It turns out x equals 0 is a local maximum, and really your minimum values occur at these 2 points here. Here we have finding a minimum area, and so we have a rectangular page. It's going to have 24 square inches of print. There's going to be margins at the top and the bottom, 1 1/2, 1 1/2, margins on the side of 1 and 1. We want to find the dimensions of the page, that is the x by y, to minimize the paper. So we're trying to minimize area, so we need an area equation. Area is x plus 3 times y plus 2. We know that the page should have 24 square inches of print, so this is our secondary equation. We solve our secondary equation for y or x, plug it into our primary, and we've got a function of one variable, differentiate it. Now if x were 0, that's also a critical number. However, clearly x can't be 0 because then you have no paper, you have no print there, and so forget about that. We just set the derivative equal to 0, and you get x is plus or minus 6, but of course we just go with 6 because negative 6 is outside our feasible domain, and then we're able to get the dimensions of our page. Here we have minimum length of a wire. We have a post of 12 feet, a post of 28 feet. They're 30 feet apart. Where do you nail this in to minimize the total length of wire? So we're trying to minimize length. We need a length function. So here we have this distance, this wire distance, and this wire distance. We can use the Pythagorean theorem to get y and z. Y comes from this right triangle. Z comes from this right triangle, where this is x and this leg is 30 minus x, because they must add to 30. So you find those two values, y and z, you add them together, and so you're trying to minimize this function. You differentiate, set it equal to 0. There's a lot of algebra, which generally we'll find ways to skip through that and not spend so much time on algebra. You get two values, negative 22.5 you can throw out. There's also the endpoint values when x is 0 and 30, and if you plug 0 and 30 back in, you do get values which are somewhat low, but they're not as low as the value when you plug in 9, so therefore you should put the stake 9 feet from the 12-foot pole. So 2 more examples in the book, but first a couple more off the web just to show you some things you can do with optimization. This was maximizing the area of a pen. We talked about that. This has to do with if you are rowing towards the shore and then walking along the beach, and the different speeds and how that should affect the route you take, and that actually leads into the Snell's law of refraction, which is something that will be talked about in the future. This is the idea of maximizing the size of a cylinder inside a hemisphere, a rectangle inscribed under a curve. We already did the idea of the point closest to another point not on a curve. Printable region, we did that. Here's our open box problem, making a cone of maximum volume, finding the biggest viewing angle. So there's all sorts of applications of optimization, but here's a couple more problems to take a look at as examples. In this problem, the idea was to find two positive numbers whose product is 192, and you're trying to maximize the sum of 1 and 3 times the other. I think it was maximized, could be minimized, I do not recall. But what we do is, here's our primary, this is what we're trying to optimize. This is our secondary, the product must be 192. I solve the secondary for one of the variables and plug it into the primary. Now I've got the primary as a function of one variable. I differentiate it. Now, if x is 0, I'd have a critical number because I'll be divided by 0. But if x was 0, it doesn't make sense because you can't have 0 times anything and get 192. So forget that. We just set the derivative equal to 0. We solve for x, and I get plus or minus 24. But I know I need to have positive numbers. That was part of the problem in the beginning. So x is 24. You plug 24 back in here, and then you get y is 8. So your two numbers are 24 and 8. And one more geometric optimization problem. The idea here was to find the dimensions of the biggest rectangle that you can inscribe inside a semicircle of radius 5. So we have some point on the semicircle at x comma y. We don't know where it is. And if that point is x comma y, then this is a distance x. Here's the distance x. Here's the distance y. So the area of our rectangle is 2x times y. So that's our primary equation, what we're trying to optimize. We want to maximize that area. So we need to get this as a function of one variable. We know that y is equal to the square root of 25 minus x squared, because that's the equation of the semicircle, so I plug it in here. Now I'm going to use the product rule, power rule, chain rule, a lot going on. So in terms of product rule, this will be my u, this is my v. So derivative of u is 2 times v plus u times the derivative of v. So first power rule, and then chain rule. The derivative of 25 minus x squared is negative 2x. I can cancel out half and 2. I have a 2 out here that I can factor out. This is the tricky part. I factor 25 minus x squared to the negative 1/2. You factor out the lowest power. Now factoring is like dividing. When you take this quantity and divide it by 25 minus x squared to the negative 1/2, you're subtracting exponents. Half minus negative 1/2 becomes first power. When you factor it out of here, it's just gone and you get minus x squared because I got an x and I got an x and a negative. Remember, this 2 is factored. So here's my derivative simplified. Now I would have critical numbers if x was plus or minus 5 because this would be dividing by 0. But if x were 5, this point would be all the way down here and you'd have a flat line. You wouldn't have a rectangle at all. So clearly that's not going to be our maximum area. So we just set the derivative equal to 0. The 2 goes away. This term goes away. So we have 25 minus 2x squared is equal to 0. You solve for x, and you get 5 over rad 2. So this is 5 over rad 2. So therefore the length is 2 of those. So 2 times 5 over rad 2 is 5 times rad 2. And then to get the height, you plug 5 over rad 2 back in here to this function. And it turns out you also get 5 over rad 2. So what you see is that actually this isn't really drawn to scale because we should have two squares joined here at the y-axis.